Atoms, the basic building block of matter. The word atom was coined some 2,500 years ago by a Greek philosopher by the name of Democritus. Democritus was the first to suggest that all matter could be ultimately broken down into tiny particles that could not be further divided. He called these particles atoms, from the Greek words meaning knot and cut. We now know that the atom itself is made of subatomic particles, so an atom can be split into smaller things. But though his wisdom holds up with a little bit of fine-tuning. The atom is the smallest bit of a pure substance to have the same properties as the same substance in larger amounts. For example, if we took a piece of iron and divided it into smaller and smaller and smaller particles, we'd finally come down to the smallest particle that still has the chemical and physical traits as what we know as iron. This is the atom. So, if we continue splitting it, it would no longer have the same physical and chemical traits as iron. Now, it was not until the late 1800s that scientists began to understand that atoms itself were made up of smaller particles. Since then, chemists and physicists have created more and more detailed models of an atom's interior. In 1897, the British physicist Sir Joseph John Thomas discovered that atoms contain negatively charged bits of electricity. He found that he could literally tear those pieces off of an atom using a strong electromagnetic force. Thomson correctly concluded that an atom must contain a positive charge, electrical charge, in order to balance its negative charge. In his model, Thomson envisioned an atom as consisting of small packets of negative electricity embedded within a large ball of positive electricity, rather like plums stuck in pudding. With this model, Thomson was the first to suggest that atoms are not indivisible, but contain parts. Thomson's negative particles are now known as electrons. So in the diagram on the left, the pink is the positive charge with the yellow negative charges embedded inside of it. Now, in 1909, another British physicist, Ernest Rutherford, went deeper into the atom structure. By bombarding gold atoms with positively charged particles, he discovered that an atom's positive charge was concentrated in a very small, heavy core, much smaller in diameter than the whole atom. If a carbon atom was the size of a domed sports stadium, its core would be about the size of a peppercorn. Rutherford called the atom's positively charged core the nucleus. In his atomic model, the nucleus was like a star, around which one or more electrons orbited like planets at various distances from the star. So in this animated model in the center, the green and orange bits is the nucleus in the center with the yellow-colored electrons orbiting it like planets. Rutherford also correctly proposed that the atom is held together by electrical attraction between the nucleus and the electrons. He later concluded, again correctly, that the nucleus is made up of positively charged particles and neutrons, which are particles with no charge. We now call these particles protons, with a positive charge, and neutrons, with a no charge. They are about the same size and held together what is called the strong nuclear binding force. Rutherford's solar system model is all one needs to understand most of chemistry and everyday physics. But two problems remain. problems remained. First, Rutherford's model allowed electrons to move in an infinite number of orbits. If this was actually so, different atoms of the same element would behave differently. They do not. Neither could his model explain why electrons do not lose energy and eventually spiral into the nucleus like an exhausted satellite sucked into Earth's atmosphere by gravity, which does happen. There are satellite ruins that are found sometimes. In 1913, the Danish physicist Niels Bohr improved Thomson's planetary model, Rutherford's planetary model of the atom. Bohr proposed that the electrons are not free to roam the atom's solar system at will, but can occupy certain orbits at specific distances from the nucleus. According to this model, when electrons absorb energy, they jump from lower to higher orbits. We now know that Bohr's hypothesis is absolutely true. In fact, the release of energy from a jumping electron can sometimes be seen in the form of packets or photons of visible light. A familiar example is the glowing light of a neon sign, produced when electricity causes the electrons of gaseous neon molecules to rise and fall from one orbit to another. And now, the fuzzy atom. The next great leap in our understanding of the atom came in 1926, when the Austrian physicist Erwin Schrödinger introduced the general concepts of quantum mechanics. According to his atomic model, orbiting electrons behave in some ways like waves, in other ways like particles. To say, they have a dual nature, having both the characteristics of both energy and matter. So like heat or light, electrons travel in waves. Like a rock, they have mass or physical substance. The practical effect of Schrödinger's quantum mechanical model is that scientists now envision electrons not as revolving in linear orbits, but as occupying energy levels or electron shells around the nucleus. In this model, one never knows exactly where an electron is at any given moment within its shell, but simply in the region where space where an electron is likely to be found. Another way to picture this concept is to envision each electron as a fuzzy distribution of electrons around its nucleus. We now know that different kinds of atoms or elements each have distinct number of electron shells. Hydrogen has one, and hydrogen is also the lightest and simplest atom. Importantly, each shell can contain only a limited number of electrons, though a shell is not always filled to capacity. The most ever found in an inner shell is 2, in the second shell 8, in the third shell 18, in the fourth 32, and in the fifth 50. When an atom shell contains its maximum number of electrons, that shell is closed. But to date, no element has ever been found in which the fifth level is filled to its capacity of 50 electrons. With the exception of the innermost shell, all can be further divided into subshells, also called orbitals, that each hold a pair of electrons spinning in opposite directions. Chemists call these sublevels with the letters S, P, D, and F. In the animated diagram on the right, it changes to show different ways the electron shells can be distributed. And now we have elements, isotopes, and ions. There are different kinds of atoms. Atoms can have different number of protons, neutrons, and electrons. Atoms with different numbers of protons are called elements. Elements all have different properties. An atom with a single proton, for example, is a hydrogen atom and is given the atomic number 1. The atomic number equals the number of protons it has. any atom with 2 protons is a helium atom, has the atomic number 2, and so on. Uranium, which is the largest of the naturally occurring, has an atomic number of 92. Fortunately, no one has to memorize every single atomic number, because there's a periodic table provided in most chemistry texts and hangs prominently in most laboratories and chemistry classrooms. The periodic table lists all of the known elements in the order of their atomic numbers. In most cases, a higher atomic numbers goes with an increased atomic mass, which is equal to the number of protons plus the number of neutrons. So the atomic mass is calculated by adding the number of protons and the neutrons in the nucleus. The number of neutrons in an atom usually equals the number of protons, but there are exceptions. An element can actually have varying numbers of neutrons. These neutron number variations are called isotopes. Different isotopes have different weights because you're adding neutrons, so the weight's going to go up. And not all isotopes can exist because if you have too many neutrons or too little neutrons, the element will not be stable. So they will be radioactive and eventually decay into a stable isotope. For example, hydrogen, it also exists in rarer forms that have either 1 neutron or 2. These different species of an element are these isotopes. They differ in mass but not in atomic number. Isotopes are all the same element, yet they have different number of neutrons. Most elements occur in nature as a mixture of isotopes, but as I said before, not all isotopes are stable. Carbon, for example, exists in 7 known isotopes, but only the carbon isotopes with 6 or 7 neutrons are stable. The other decay or lose their extra neutrons to reach a more stable form. When chemists list a given element's atomic mass, they actually average the atomic masses of all of that element's naturally occurring isotopes. As a result, the atomic mass is seldom a whole number. The atomic mass of hydrogen, for example, is 1.0079 to reflect its rarer isotopes. An atom can also have different numbers of electrons. If the electrons equal to the number of protons, the charge of the atom is 0. It has no electrical charge. For example, if we have a hydrogen atom, if it has 1 electron, it will have a charge of 0, because the negative charge of the electrons cancel out the positive charges of the protons. If there are more electrons, there will be a negative charge. If there are more protons, there will be a positive charge. More electrons means more negative packets of electricity, so it will overwhelm the proton's positive charge, and the overall charge of the atom will be negative. Same for protons.